So Karunya is going to talk to us from LSU, works with Julia Vector, is going to talk to us about tuning topological properties, one step towards 2D quantum computing. So thank you very much.
Okay, it's working. Okay, hi everyone. Today I'm going to be talking about tuning topological properties towards quantum computing. So topological insulators are materials that are insulating in the bulk, and they have what are called topologically protected surface states at the surface. And I think one of the premises of topological quantum computing is that information can be encoded in the braiding of anyons. And now there's a class of materials that is predicted to host anyons, and topological superconductors are one of these materials. So in topological superconductors, there is a vortex lattice, and the vortices in these lattices are topological defects that have integer phase winding, and they carry quantized magnetic flux. And the anyons in these materials are in the vortices, and they're trapped there. And so that's one class of systems which can host anyons. But topological superconductors are hard to observe experimentally. So an alternative has been proposed in which one sets up a heterostructure of a topological insulator and a superconductor, and we apply a suitable magnetic field. And in this case, superconductivity is induced via proximity in the topological insulator, and the topological insulator has protected surface states. And this combination ends up being something like being the property that it ends up being the property that's the reason these states are resistant to decoherence. And that's why these materials are supposed to be useful for fault-tolerant quantum computing. So topological insulators have an important property, which is a strong spin-orbit coupling. And they also have an important symmetry, which is called time reversal symmetry. So in time reversal invariant materials, the electronic states at momentum k would spin up and momentum minus k would spin down are degenerate at special momenta, which are called time reversal invariant momenta. However, at other crystal momenta, spin-orbit coupling in these materials leads to these two states being non-degenerate, which means that at a given energy, there's only one state. And thus, if one thinks about scattering, there is no state for like an electron at a given energy to scatter into, which is why the spin of these states is locked to the momentum. And that's what we refer to as spin momentum locking in these materials. So in the figure on the left, I show the helical surface states in real space of these materials. So we can see that like electrons with opposite spins, which are represented by the small gray arrows, are traveling in opposite directions around the slab of the material. So in the middle figure, I show the Dirac-like dispersion of these states. So we have the energy versus the momentum, and it again shows the helical nature of these states. And in the figure on the right, I show the surface states of bismuth selenide, which is one of the prototypical topological insulators, observed using the experimental technique ARPES. So for the bismuth selenide family of materials, there is a microscopic model or a Hamiltonian, which is built starting from the atomic p orbitals of these this material. And so the authors who came up with this model considered the chemistry of the system, meaning they considered various effects such as atomic hybridization, crystal field splitting, etc. And they found that the two levels which are closest to the chemical potential in the system are the bismuth and selenium PZ levels. So they're the Z projection of the P orbitals of these atoms. And this is like we're looking at stage 3 in the schematic figure. And then what happens is when you include spin orbit coupling in your picture, these two levels exchange positions with respect to the chemical potential. And this is what's called band inversion. And that ends up being the reason for the topological nature of these materials. And these two levels, or rather all of these levels on the rightmost panel, play the most important role in giving rise to the low energy properties of the system. So this model, which I talked about previously, relies on various parameters, such as the initial splitting between the bismuth and selenium p orbitals, etc. But we do also want a way to capture the physics without using these parameters, because we might not know them, which is why we use what is called density functional theory. So density functional theory is a first principles technique that transforms a many electron problem into a set of single particle non-interacting equations. And in the equation which I show you, that's the single particle equation that needs to be solved. And density function, okay, so what happens is if one were to try and solve the full many electron problem, if you have n electrons in a system, you're going to have an electronic wave function which has 3n variables, which is a very large number of variables, and it will be very computationally intensive to solve. But instead, it transforms it into a problem where everything depends just on the electron density and not the and not on each individual electron's position. So you just have 3 variables instead of 3n variables. So the one important thing to keep in mind is that while density functional theory itself is an exact theory, there is a term in that single particle equation which we don't know, which is the one circled, which is called the exchange correlation functional. And because we don't know it, we need to come up with some sort of approximation to it. So some of the common approximations include what's called the local density approximation and the generalized gradient approximation. So in the LDA, they assume that this exchange correlation functional depends just on the electron density at a point. And in the GGA, it assumes that that functional depends on the electron density as well as its gradient, and so on. There are various approximations to it, but these are the 2 common ones. And they end up working quite well for a lot of materials. However, it is hard to include longer range interactions, such as the van der Waals interaction, which is known to be important for the bismuth selenide family of materials. And so van der Waals interactions basically arise from dynamic polarization of electron densities of atoms, and they lead to the formation of instantaneous dipoles in these materials. And the dipole-dipole interaction goes as 1/r⁶, as we studied in E&M quite a while ago. So in density functional theory, there are 2 main ways to include the van der Waals interactions. These consist of something called the semi-empirical methods and the van der Waals functionals. So in the first class of methods, DFT adds an energy correction to the total energy, which goes as 1/r⁶, corrected by some coefficient Cij for every pair of atoms, I and j, in the system. And the van der Waals functionals, on the other hand, they actually modify the exchange correlation functional to include the van der Waals interactions. So one of the important ones is going to be what's called the DFT-D2 technique. So on the right, I show the crystal structure of these materials. So the crystal structure consists of sets of 5 atomic layers called quintuple layers. And that's shown in the box on the right. And another important quantity which is going to come up is called the interquintuple layer distance, which is marked in orange. So the quintuple layers in these materials are held together by weak van der Waals forces. So when we started out running our calculations, we found that most calculations keep the lattice parameters fixed without optimizing them. And the reason is that some of the lattice parameters, especially that distance between the quintuple layers, are significantly different from experimental values if they aren't fixed, and we optimize them ourselves. However, this is a problem because DFT itself is a ground state theory. So we could end up obtaining what are called metastable states if we end up fixing the lattice parameters. So what we did was we set up a way of performing first principles calculations on these materials where we obtain the bulk and the topological surface state properties accurately. And so what we did was we compared like a couple of different methods of including these van der Waals interactions in DFT calculations on these materials. And we found that that method, which I'd mentioned earlier, the DFT-D2 method, is the most accurate, and that the R to the 1 over R to the 6 term is significant. And we were able to reproduce the Dirac velocity, which is, okay, I'll talk about that in a minute. The Dirac velocity of these topological surface states quite accurately for both bismuth selenide and bismuth telluride. And we were also able to obtain what's called the hexagonal warping in the surface states of bismuth telluride. So in the figure on the left, I show the topological surface states of bismuth telluride in blue. And the part near where these two blue bands cross is called the Dirac point. And the velocity is the slope of that state. I mean, the Dirac velocity is the slope of that state close to the Dirac point. And in the figure on the right, I show the same states, but in this, I've plotted their spin texture. So if we go back to like if you remember the slide at the beginning where I showed the helical structure, close to the Dirac point, we find that the spins are all in the plane. So we just have like a circular dispersion, which is the bottom left panel in panel B. But as you increase the energy, the dispersion becomes hexagonal, and then it becomes almost star-shaped. And the blue arrows, which represent the spins, they start pointing out of the plane. So the spin momentum locking changes as you go away from the Dirac point. So we now have a methodology to calculate the structural and the electronic properties. And we were able to obtain the properties of the bulk, such as the lattice parameters and the band gap, and properties of the surface, such as the Dirac velocity and the spin texture properly. So moving forward, we next asked the question of how strain affected the topological properties in these materials. So starting off with bismuth selenide, what we did was we fixed the C over A ratio of lattice constants. So in the crystal structure, the C axis is like along the Z direction, and the A lattice constant is in the plane. And what we're doing is fixing that ratio and relaxing it such that the hydrostatic pressure in the system is minimized or becomes 0. And what we found was that as that particular ratio is increased, which is kind of an equivalent method to applying strain on the system, we found that structurally, the quintuple layer, which was that set of 5 atomic layers, remained almost intact, whereas the distance between them increased. And electronically, we found that the band gap in these materials decreased, and then it closed at some point, and then reopened, but the band inversion was lost. So if you recall, the band inversion is the important property which is responsible for the topological nature in these materials. So if the band inversion is lost, then the topological protection or the topological nature is lost. So it's a trivial material at that point. And what we did was we used this band inversion as a signature of the topological nature of these materials. So in the figure on the left, in the top 2 panels, I show the band structure of these materials projected onto the bismuth p band and the selenium p band. So in panel A, we can see that near the gamma point, which is at the center, the band just below 0 comes from bismuth p, and the band above 0 comes from the selenium p. Whereas if you apply considerable strain on the material, in the bottom panel in C and D, the bismuth p is now above 0, and the selenium p is now below 0. So they've exchanged positions, and so that's the bottom panel C and D shows a trivial system, whereas panel A and B show a topological system. And this is what, so we carried out this investigation for the whole family of materials: bismuth selenide, antimony selenide, bismuth telluride, and antimony telluride. And what we found was that all of them show this similar topological phase transition as the C/A ratio is increased. And the important thing that we found was that it was the physics between the quintuple layers which seemed to be driving the transition mostly, as opposed to the physics of what was happening within the quintuple layers. So in the figure, in the bottom figure on the right, I show the evolution of the bismuth PZ and the selenium PZ levels, which are the same levels we've sort of been talking about from the beginning. So in the beginning, the red triangles, which are the bismuth PZ levels, are considerably below the selenium PZ levels, which are the blue squares. And as you increase the C/A ratio, which amounts to applying strain, they start getting closer together, and at some point they exchange, they flip, and beyond that point, it's a trivial material. Whereas initially, for low values, towards the left of the graph, you have a topological system. And okay, I'll just skip this. But the emergent picture that we found was that it was basically the Coulomb repulsion between adjacent quintuple layers, which competed with the van der Waals attraction between them. And this competition was basically driving the transition. And one interesting thing that we found was that at the critical point at the transition in each of these 4 materials, there was a universal value for the distance between atoms. So this is shown in the table, in the rightmost column. So we found that there was a critical distance of about 2.8 angstroms, for the atomic spacing between quintuple layers. And this is interesting because this can be measured in experiment. So it can have an experimental signature as well. Okay, so now that we had a picture of what was happening as we applied strain, we also finally started looking at what would happen if we alloy different topological insulators. So we were introducing disorder in these materials. And okay, so the backstory, I am kind of out of time, but the backstory is that one of these family of materials, antimony selenide, was initially predicted to be a trivial insulator, and which is why when you alloy it with a topological insulator and you vary the relative concentration of the two, one would expect that at some point there's a transition from a topological to trivial state because you're kind of mixing them and varying the concentration. So we were trying to pinpoint that concentration at which that transition happens. And I won't get into the details, but what we found was that at a 50% concentration, first of all, we found that both the endpoint materials, which were bismuth selenide and antimony selenide, were both topological, sort of in contradiction with the previous results, which said that antimony selenide is trivial. Okay, this is not like a very novel result on our part. This had been found before, but we did find that at concentrations in between, it is trivial, which indicates that, so if you have a phase diagram in which the endpoints are both topological and the middle is trivial, that indicates that you have at least two transitions from topological to trivial and then trivial back to topological at some intermediate concentrations. So we're exploring this phase diagram right now and trying to pinpoint where exactly the transitions take place. But overall, what we were doing was trying to find different ways of tuning the topological properties of these materials, which is necessary for technologies which are based on these materials. So one of the ways that we were tuning the properties was strain, as I just mentioned. And then another way to tune it, to tune the properties is through disorder. So is through introducing disorder in these materials. So yeah, in conclusion, what we did was we first set up this framework in which we reproduced the bulk and surface properties. And then we explained the physics of the transitions under strain. We found it was due to these competing Coulomb and van der Waals interactions. And then finally, we're studying disorder now, and we've sort of set up a foundation to study other problems involving these topological materials. And that's it. Thank you.
Thanks very much.
Yeah.
I have two kind of broad questions.
Yes.
You might have said it already, but what are topological materials useful for besides quantum computing?
Okay, so, well, right now, I think most of the, at least for topological insulators, as far as I know, most of the proposals are towards, are based towards like maybe creating these heterostructures and like observing these anions in them. But
It's like interesting physics.
yeah, but I think another thing that they could be useful for is spintronics. So because they have this important property of spin momentum locking, which means that if you kind of are able to control one of those degrees of freedom, you'll be able to control the other one as well. So if you're able to like have a way to change the momentum, you will be able to change the spin. And then spintronics is basically based on using the spin orientation, I think, as like the control. Yeah.
Right. My other question is, do you have any idea whether some of the calculations you're doing in your work could benefit by having a fault-tolerant quantum computing?
Well,
Like a quantum algorithm.
yeah.
You know, a lot of people are using, they want to use quantum computers to understand materials, etc. I think in your postdoc, you might be doing something.
Yeah. Well, so there are calculations. So, okay, a lot of these, I'm not sure if this will work out, but so a lot of these calculations are like massively parallel. So they require like supercomputers. So maybe if at some point there's like an implementation of parallel computing on quantum computers and it reaches that stage, maybe they could be run based on that. I don't know.
Right. I mean, it's open.
Yeah.
think the related question to what Mark asked. The exchange correlation function, that's the real problem, right? With DFT.
Yeah.
So, of course, if you consider van der Waals forces and sort of weak correlations, it works out because you can sort of write it in closed form. You guess it's 1 by R6 and
Yeah,
almost always works.
Yeah.
But for example, in the case that you were showing, so I remember there was this the p orbital splitting,
Mhm.
right? Is it known that that splitting occurs not because of strong electron correlations and just because of weak correlation?
Yeah. So at least in these materials, they are so bismuth and selenium. They don't have. So you usually have strong correlations when you have heavier atoms and like F electrons and things like that. So in those materials, you do need to be careful about doing DFT. So you sometimes need to include like some kind of we call it the Coulomb, so some kind of like either exchange parameter, or we need to include a Coulomb interaction. But in these materials, the correlations are very weak, so you can use DFT. But yeah, it's true that for materials which have strong correlations, just DFT won't work. You'll have to include some special corrections.
Somehow find the exchange correlation. Therefore, I was asking,
Yeah.
can you somehow use quantum computing and so on?
Yeah.
To actually.
Maybe. Yeah.
It's kind of a quantum simulation problem, right? Because you have these electronic systems, and if you simulate them exactly, then of course the electron-electron correlation is there.
Exactly.
Now it's
Yeah.
a question of can you derive the exchange
Yeah.
correlation function from
Yeah.
I don't know.
No, I mean, that's possible. Sorry, there was one more question. Yeah.
In your DFT plus D2 calculation, which functional did you use?
It's just GGA. So we use the GGA exchange correlation functional, and then we add this correction on top of it.
Okay. And another question, in the plot that you show the energy gap versus the C/A, can that transition be measured experimentally?
Yes, yeah. So okay. So one thing is that this is calculations for a bulk material. So it might be slightly different. Like the value of C/A might be slightly different if you're looking at a thin film or something.
Sure,
But yes, it should be. Yeah, you should be able to.
Have anybody
Um,
observed this experimentally?
I think. I'm not entirely sure, because the thing is, the particular way in which we implemented strain, or we were looking at strain, was this C/A ratio, which is one way of doing it. But experimentally, it's kind of, I think, hard to vary the C/A ratio. So experimentally, like you just have the material and you're applying some kind of strain on it. So we'll end up there with a slightly different strain, like a uniaxial strain. Instead of this particular way in which we were calculating it. But I think like experimentally people have done the uniaxial strain and they have found the transition. So it's slightly different, but it's similar. Yeah. Okay.
All right. Well, thank you again.
Sure.
So 11.